Welcome back. I'm Larry Benko, W0QE, and recently I had an online discussion and difference of opinion concerning the usefulness of number 31 material toroids for high-power applications in the HF frequency range. I thought it would be appropriate to make some measurements and do some simulations to help understand this topic, and thought others might find it interesting also. Number 31 material has become the de facto standard for receive and low-power transmit use when trying to reduce common mode current associated with RF interference and RF susceptibility. The low Q nature of the choking impedance and the high impedance overall is highly desired. However, fewer types are available in number 31 material. I don't believe to date there are any binocular type cores made in 31 material, although I could be wrong. But there are certainly more types available in number 43 material than there is in number 31. But what I decided to do for this experiment was to take some cores that I'd purchased from Ferrite Corporation a year or two ago. They're Ferrite number 2631803-802, which is the same as an industry standard FT240. So it's 2.4 inch outside diameter, 0.5 inch high, 1.4 inch inside diameter. And I wound some very high temperature TEF-Zel type coax on them. And I started with about 18 turns, and I kept reducing a turn or two at a time and remeasuring them. And I ended up with two different specimens to use for a test, 11 turns and 14 turns, and I'll show the reasons for those in a minute. What I did was try to see how much power and how much voltage I could put across this representative core, and then I would scale the core size as necessary if I needed to or whatever. SimSmith is very well suited to analyzing this type of a problem. And what I have here is side by side the 11-turn impedance file and the 14-turn impedance file, both of them being driven from a generator. And what I'm looking at here on the Smith chart is the impedance of both of them. We see the pink plot is the 11-turn one, and slightly higher impedance is the 14-turn plot, which is the blue one. And we can look at that a different way if we wish. I did some plotting here on the square chart to plot the real part, the imaginary part, the magnitude of the impedance, and the Q for both of them. And then I colored them all blue. So the resistance of the 11-turn core, as we run from 1 to 60 megahertz, which was the scan frequency, rises to about 4 kiloohms maximum. And the reactance is shown here with the resonant point being about 6.1 megahertz or something like that. The magnitude of the impedance rises so that it's above 3 kiloohms by the time we get to the bottom of 160 meters. It stays 3 kiloohms out through just about 20 megahertz. And the Q, it's hard to see. The Q is low here, less than 2, goes through 0, and I show it as negative because I didn't change the reactance, and the reactance is capacitive here. And if we look at the 14-turn core, we see it has higher resistance. It has higher reactance, but it goes through resonance sooner. And consequently, it has lower impedance out here at the higher frequencies by a little bit. Again, the Q is low everywhere, a little bit higher out here because of the extra capacitance that it has. But realistically, both of these have very, very high impedance. Now, one other thing before I do anything else is to look at this. And this was a calculation. If I was going to drive these cores ultimately at legal limit, I could generate 274 volts, and that would be driving the 11-turn core at a level of 50.7 Gauss. They are rated typically for 57 Gauss, so 50.7 I expected to see reasonable heating. The other thing is the formula for inductance and for the flex level both have A sub E in them. A sub E is the cross-sectional area of the core, which means if I needed another core to stack in series with, stack on top of the first core, I would be able to say that core would have half the flux in it that the first one had. It would have twice the impedance. Now, it doesn't work exactly like that as the resistance piece gets involved here, but keep that in mind because we may need to use a second core or third core or something if the core heats up too much. And here I take the same two coils again, wound the 11 turn and the 14 turn, I have a generator, which is a 1500 watt generator. It's matched to whatever impedance I would have, but it turns out to be a very good impedance because the impedance of these two coils are very, very high. And I drive a dummy load, legal limit dummy load, legal limit amplifier, and I put the voltage across the coil. It turns out that the heating effects in coil are related to the voltage across the coil only, not the current through it or anything else. The overall temperature rise is a function of the voltage across the coil and the wire itself. In this case, the wire has very little current in it because of the fact that it's very high impedance. I was trying to measure just the core temperature alone due to heating, due to the loss in the core. I plotted the two from 1 to 60 megahertz, and the 11-turn one, which is R1, we see its loss goes from about 14 watts up to a maximum of about almost 18 watts and then back down again. The one with 14 turns has lower loss everywhere. This is plotted on a log scale. I plot it linearly. It doesn't matter. And it starts to rise up here. So ultimately, the 14-turn one has less temperature rise, but it rises to highest temperature at 6 meters, which is 13.85 watts. The 11-turn one has its highest temperature rise at 7 megahertz, just a little bit below it, but I can't transmit there. So at 7 megahertz, it's got just about 18 watts. So I decided I'd do a test based on the 11-turn one and see where 18 watts actually resulted in, what kind of temperature we would get. And then I could scale it back if I needed to. And if I needed more voltage, I'd have to figure out a different circuit to use for that. And here we have the test set up. I've got a 100 watt exciter running about 40 watts, driving an alpha 8410 amplifier to legal limit or just a little bit above. The tests were involved. All the tests had the output of the amp between 1500 watts and 1550 watts. A watt meter, a dummy load, good for legal limit forever, and a piece of coax that goes from the amplifier to the dummy load, but with a tap right here so that the coil that I wound is across the line. So it sees the full line voltage, but remember it's very high impedance again, so it does not disrupt the SWR on the line, but the coil does see the full line voltage. And shown a little more closely what I did to measure temperature, I have a type K thermocouple with a little bit of heatsink compound wedged under one of the turns. I have some temperature indicating paint that is set for 105 degrees Celsius that melted. Ultimately, I have a piece of black tape that I use a spot infrared meter. I've got an infrared temperature meter that's got a 1/8 inch spot on it, and I have a black piece of flatback black paint I painted on the core. Now, it turns out that all four ways of making these measurements did not result in the same answer. Ultimately, what I ended up doing was using the temperature probe as the number one case, and I dropped water on here, just little teeny drops from a pipette, and can see when it got to 100 degrees Celsius, and a little bit afterward, this melted at 105 degrees. This is very accurate temperature indicating paint. The infrared thermometer never read very well. It always read about 10 degrees lower than the type K thermocouple or the paint or the boiling water. So I used those three, which matched very accurately. When the thermocouple said 100 degrees C, the water boiled. Actually, the water boiled a little bit below that due to our altitude here, but the temperature indicating paint at 105 degrees matched when this said 105 degrees very accurately. And it's hard to measure the temperature of these cores. They're inside, they seem like they're really solid, but they're very, very much like a ceramic material. And the surface on them cools down very quickly, but the inside stays hot, so they're a little difficult to measure. But nevertheless, the Curie temperature is 130 degrees Celsius. I wanted to stay below that. And the results are shown here now. And we see that 6 minutes of continuous key down, 1500 watts, caused the temperature to rise to 105 degrees C. And it got to about 100 degrees C in about 3 minutes, and it took another 3 minutes to get to 105. So maybe ultimately it was going to get to 110 or something, but I stopped at 6 minutes. And then I went and I sent 50% dots, again at legal limit, which would be 750 watts, and the temperature dropped to about 86 degrees Celsius. And again, this is due to the excitation due to flux in the core, not due to wire. The wire does not have any current in it. This is not run like a Balun or anything. This is just run as an inductor, but it does get the same flux level. So anyways, I thought that was very interesting. And because of that, I kind of concluded that maybe the core is good for something along the lines of about, at full key down, the core was seeing 18 watts. At 50% duty cycle, it would see 9 watts. And 9 watts seemed like a fairly reasonable number to have in the core. Maybe even a watt or two less than that if you were going to heat up the core slightly due to the wire itself. But 8 or 9 watts seems like a reasonable amount of power dissipated in these FT240 size cores. And now that leaves us with just one more thing to do, and that is to put a Balun in a circuit and measure what the common mode voltage across the Balun is and what the power will be in the Balun due to the flux in the core. And we can do that fairly easily by using one of two circuits. The first circuit is a circuit that comes out of classical textbooks on how to model Baluns, and the second one is the circuit I've been using. Both of these produce very close to the same results, but I think this one is more accurate. This one starts to have problems when the length of the transmission line here is very long and these two voltages become different. And I've used it because for the most part it's an easier circuit to do than this, but let's use the more complicated one for this example. And SimSmith is doing both of them simultaneously at the same time. It's got two circuits. It's just got two Baluns that are done modeled differently, and two sets of results. The A set of variables goes to the A ruse block, and the B goes to for the B block. And what I want to do here is 1.3. What I've loaded here in this circuit is an impedance file which represents the common mode impedance of the Balun, which is the 11-turn Balun. You can barely see it right there. You may not be able to read that. Let me hover over it. You can see up above, up here. You can see it's the 11-turn Balun, and it's the same for both. And what we have here is we have an ideal transformer, which is incredibly high inductance, so it doesn't affect the circuit. We strip off the common mode current here, pass the common mode current through that impedance back to this side. We let the differential stuff go through this way, through the transmission line, and this 1 gigohm resistor to ground is needed because SimSmith has done a pretty good job of putting 1 gigohm resistors to ground to keep you from having problems like LT Spice does when you model. But in this case, I needed one. At least I think I needed one. By having this isolated from ground, you end up with matrix problems in the calculation. So what we have here is three impedances. They're shown as resistors, but they're actually complex impedances, which represent what your antenna is at each frequency. And you can come up with these numbers by making a set of measurements, 3 different VNA measurements on your antenna, and you can come up with these values and put these in as files if you wanted. You would know exactly how your antenna would work with a Balun. The work for this has been done by people like Kevin Schmidt, W9CF. On his website, he describes it. I've done this in LT Spice. I've also done it in SimSmith several times, and I could do another video on this, but it's out of the realm of this video right here. We'd be here for another hour to do that. However, what I have here right now is a piece of transmission line that's 1.3 feet long, which is what the piece I wound across the 11 turns was. And we'll set the common mode impedance to be 0, which is the worst case. Now, all real antennas have a common mode impedance out here. They do not look like just some resistance or some impedance out there in space. They look like they have some connection to ground. It may be a high impedance, but they do have some connection. And we'll assume that we're going to drive a 50 plus J0 load. And since it's set to 0 ohms here, I'm going to put the center point at 50%. And the transmission line is wound with 50 ohm coaxial cable in it. It's not a transmission line. The choke is wound with 50 ohm transmission line. And let's look at the voltage we would get when we're driving this with legal limit, 1.5 kilowatts. And that's a plot right here, which shows a voltage of 136.4 volts, which is just half of what the RMS voltage is coming in from the amplifier at legal limit. And the reason for that is we need to take this 0 to 274 volt AC signal and make it really 136.4 to minus 136 plus and minus volts. So we have to offset at 136 volts, which means we need 136 volts across our Balun. And it doesn't matter whether there was a tuner on this side of the Balun or on this side of the Balun. Or let me say, it doesn't materially matter. It matters a little bit because if your matching network has choking impedance in it, that will affect this number a little bit, but it doesn't affect it a lot. We're going for very high choking impedance here, so the other stuff that we put in the circuit really doesn't matter much, including this common mode impedance doesn't matter nearly as much when we have this be 2,000 or 3,000 ohms as it does when we have this only be a few hundred ohms. So there's our number, 136 volts. We can also look at the power now the power in the Balun, and that shows as 4.4 watts at 7 megahertz. And before we said we could have up to maybe 10 watts. That would indicate that if we were driving a low SWR load here with a Balun that was built with transmission line that had the same impedance as approximately the load, we would be just fine with one FT240 core. Now, what happens if we want to drive all 2-to-1 SWRs? Do we get in trouble? So a 2-to-1 SWR would be like maybe 100 plus J0. That raises that to a maximum over the HF range of about 8.82 watts. That's getting close to what I said was the maximum you wanted to see if you're going to run a high duty cycle type operations. What about 25 plus J0, which is also 2-to-1 SWR? It doesn't have as much heating effect. How about 40 plus J30, which is another 2-to-1 SWR? There we're at 6 watts rising maybe to 7.7. 40 minus J30, another 2-to-1 SWR. That's better. It's very interesting to play with this. I've played with this particular circuit probably for 2 days now, for a total of maybe more hours than I would probably want to admit. And it's very, very interesting. It's kind of mesmerizing and it's a lot of fun. What happens if you no longer have an antenna that's primarily a low SWR antenna, but you have maybe like a random length dipole fed with some kind of open wire line? You have wild variations of load impedance being presented to your Balun. Let's suppose you had 400, I don't know, minus J400. That's now is a voltage that's somewhere around 500 volts and a power in the Balun of 64 watts. Well, that clearly isn't going to work. You're going to set that Balun on fire in very short time. So what you're going to need to do then is either add more cores to be able to tolerate this kind of power, or you're going to need to get the choking impedance higher and higher and higher to drive this down lower. The power down lower. This heating is due to I squared R for the current that flows through the common mode impedance. And the goal is to make R higher and higher and higher. You can't make it low with 31 material. 31 material just has too much R to begin with. So you have to make R so high that I drops. And if I drops, then I squared R drops. That's kind of where you're at. What's happening here is we are stuck with we're stuck in a position here where one core is good enough to work sometimes, but not other times. But if you don't know what you're doing, you could easily be in trouble. So in this case, we would need to have multiple cores. You can take this as far as you'd like. If you like this kind of video, I could continue on with this discussion somewhat. If it's just not of interest or it's too complicated, just let me know. That's fine too. I will make the files available. If you want to play with them, feel free to do so. If you have a better schematic or a better circuit that you think models a Balun than this circuit, please let me know. Again, this is only is true for a single winding Balun, not for any kind of transmission line transformer, which would be a different circuit and more complicated to do. But I do believe this models it appropriately. I have measured, to the best of my ability, various data points, and I got the right results. The other thing you might have wanted to have done, if you were running something like an impedance like this, you wouldn't have run 50 ohm transmission line through here. You might have paralleled up a couple wires and run maybe 100 ohm or 200 ohm, 150 ohm transmission line. Turns out it didn't make any difference, really. Just changed it a little teeny bit. It made some improvement up here at the high frequencies. What if the length of the line, if you're going to wind your choke through more cores, you can't do it with 1 foot, 2 feet, 3 feet. 4 feet. You know, you get places where the Balun is running ice cold and other places where it's running pretty warm. So anyways, let me know what you think. And as usual, there'll be more videos, but hopefully this has been interesting.